Hi, so today we're going to be talking about average rate of change. Now, average rate of change is really not that difficult to do. In fact, without knowing it, you've probably been doing it for a long time already. Really what we're looking at is how is one variable going to be changing with respect to another variable. To do that, I've kind of set up a graph for us to look at initially. And what I want to do is, here's our function f, kind of a parabolic curve. We don't know it's a parabola because we don't know how this thing behaves outside of what we're looking at here. But I've identified a couple of points here. We're going to talk about the point x, and we're going to talk about another point called x plus h. So in other words, we've added h units to get from one x value to another. Those are the two x values that we're going to look at. And what we want to do is we want to find out, on average, how quickly is this function f changing as I move from this x value to this x plus h value. The first thing I need to have in order to be able to do that is I need to know what is the actual function value at those 2 points. So I'm going to look at this over here, and the first thing I'm going to do is I'm going to identify what the y-coordinate is for those 2 points. If this is my function x, I don't know a specific value. I'm not going to be able to calculate anything. So we're talking about a really general situation here. So we'll just call that point, that's going to be the point f evaluated at x. And for this point here, moving that across, if I mark that on the y-axis, that's going to be the function evaluated at the point x plus h. And what we want to do here is we want to find out how much the y variable is changing with respect to the x variable. So every time the y value changes, every time the x value changes, how much is the y value changing? To do that, I need to find the difference between the y values, because that will tell me how much the y value has changed. And so if I evaluate that, that's going to be f of x plus h minus f of x. That will tell me how much the y value has changed, and I'm going to divide that by how much the x variable has changed. So in this case, that's going to be the x plus h value minus the x value. Okay, so change in the y value divided by change in the x value. Now, that should sound pretty familiar to you. Change in y divided by change in x. We've been doing that since Algebra 1. We called it slope. Really, that's what we're talking about here. Average rate of change is slope. So this is where this kind of goes. It's also why we spent so much time in Algebra 1 talking about slope, is so that we can get to this point and start talking about average rate of change. We're going to actually, in our next video, start talking about, well, how can I find out how quickly something is changing at a particular moment? In this case, all I can really do is I can find, on average, between the point x and the point x plus h, how quickly is this function changing on average over that interval. Now, it's important for us also to keep in mind what are units of measurement here. Keep in mind that my numerator here is based on the y-coordinate, and I've identified that as liters. So whatever this turns out to be, the unit of measurement in the numerator is going to be in liters, and I've identified the unit of measurement on the bottom as feet. So down in the denominator here, my unit of measurement will be in feet. That tells me that whatever result this gives me, I'm going to be able to find the rate of change in liters per foot. Okay, a rate of change. So it makes sense that we're talking about a rate of change. My units of measurement reflect that as well. So let's take a look at maybe some specific examples here of finding average rate of change. I'm going to do one with an actual function, and then I'm also going to do one with a table of data as well. So let's take a look at a function value first. Let's say that we were given a function. Let's do f of x equals, let's say, 2x squared minus 3x plus 4. And let's say that I wanted to evaluate that or find the average rate of change from x equals 1 to x equals 3. How much is this thing changing from x equals 1 to x equals 3? Okay, to do that, what I'm going to do is use my average rate of change formula. I'm going to do the f function evaluated at one point minus the f value evaluated at another point. Really doesn't matter which way I do that, but whichever way I do it, I have to make sure I remain consistent, just like when we were working with slope way back in Algebra 1. So there's my change in my y value divided by my change in the x value. So really all we're doing here is finding the slope of the line that connects the point at x equals 1 to the point at x equals 3, the slope of the secant line. Okay, so really quickly we can evaluate that. 2 times 3 squared is 18. Plugging in 3 into the function here, 3 times 3 is 9, plus 4, minus, and be careful here, make sure you're subtracting the entirety of f of 1. If we plug in f of 1, we get 2 times 1 squared, which is 2, minus 3 times 1, plus 4, all divided by 3 minus 1, which is 2. Now we can do some really quick calculations, and I find that's 18 minus 9, that's 9, plus 4, which is 13, minus the quantity 2 minus 3, that's negative 1, plus 4, which is 3, all divided by 2, and I find that I get 10 over 2, which is 5. So my average rate of change for this function from x equals 1 to x equals 3 is going to be 5. And again, if I know the units of measurement for the x variable and for the f of x variable, like maybe x is given in time, maybe seconds, and f of x is given in miles, then this would be a result in miles per hour, a rate of change. So on average, from time equals 1 to time equals 3, the function, whatever it is that the function is representing, is changing at a rate of 5 miles per hour. Okay? So really simple, basic concept. It's what we've been doing since Algebra 1. Nothing's changed about that at all. We're still just talking about slope. We're talking about the slope of the secant line that connects 2 points on some graph f. Now, sometimes when we're working these things, we don't have a full set of data. Sometimes really all we have are points to work with, and that's where the table of data comes into play. So let's say that I had a table of data. Let's say that, and I'll put some units of measurement with this one. Let's say that we've got a car that's moving in time, and the position of the car, we'll call that function s of t, is given in miles. So t is given in hours, s of t is given in miles, and let's say that after 1 hour, the car is, let's say its position is 10 units to the right. After 3 hours, let's say that the car is 41 units to the right, and then let's say at 7 hours, the car is, let's go 93 miles. Okay, so we want to find the rate of change, the average rate of change of this car as it's traveling over, let's say that we want to approximate the instantaneous rate of change, or exactly how quickly this car was moving at this. So we're going to approximate the instantaneous rate of change at, let's say, time equals 6. Now, for right now, I don't really have a way to find the instantaneous rate of change at time equals 6. I can't tell you right now exactly how quickly that is. What I can do is use the information that I have to find how quickly the car is changing on average between 3 and 7. That should give me a pretty good estimate or approximation of how quickly this car is moving at time equals 6. Now notice that I could use 1 and 7, how quickly the car is moving between hour 1 and hour 7, but that approximation is not going to be as good as using 2 points that are as close as possible to the point that I'm actually interested in. So just like with the table of, or with the function that we had, I'm going to evaluate. Sorry, I changed the name of the function. We're working with function s. So we're going to evaluate s of 7 minus s of 3, the change in my dependent variable, divided by 7 minus 3, the change in my independent variable. So I'm using the average rate of change, or the slope of the secant line, from 3 to 7 to approximate what's actually happening exactly at time equals 6. And when I evaluate this, I'm just pulling data from the table. S of 7 was 93. S of 3 was 41, divided by 7 minus 3, which is 4. And of course, I can subtract that, and I get 52 divided by 4, which will be 13. And remember, this was in miles, this was in hours, and so now I know that this was a relatively slow-moving car moving at a rate of 13 miles per hour at approximately that rate at time equals 6. So I don't know exactly what's happening at time equals 6 yet, but I can use the average rate of change to get a pretty good approximation for what's happening at that time. But the next thing that we're going to look at is how can we actually find what's happening at exactly time equals 6. That's how we're going to find the instantaneous rate of change. That's a topic for our next video.